Okay, so we're going to begin our review here for the first test. So we're going to start with one of the first topics we talked about, which was acceleration. So, basic definition for acceleration, we actually had two. It is the rate of change of the velocity. Okay, that's one definition of acceleration. Or how quickly an object speeds up, slows down, or changes direction. Okay, so those happen to be the three ways we can accelerate, and acceleration is really a measure of how quickly that occurs. All right, moving on, link between velocity and acceleration. Objects are speeding up if v and a are in the same direction, and they're slowing down if velocity and acceleration are in the opposite direction. Okay, so we talked about that a lot with our vectors, right? When velocity and acceleration are fighting each other, we are slowing down. When they're going in the same direction, even if that happens to be the negative direction, we're speeding up. Calculating our acceleration, okay, in order to do that, we are going to do acceleration is v final minus v initial over time. Okay. Some tips to keep in mind when using that particular formula. One thing we want to think about are signs, of course. Those are always going to be important, but we also want to think about proper units. Okay, so keep in mind that acceleration should be in meters per second squared, velocity should be in meters per second, and time should be in seconds. Okay, so we want to make sure we have those units when using that formula. One last thing to keep in mind, and this was a distinction we talked about a lot, and this is something that I know is tricky, especially when we get into those speeding up with a decrease in acceleration type problems, but this difference between speed and velocity versus acceleration. So keep in mind that speed and velocity, we're really thinking about how quickly position changes or how fast we are going. That's what speed and velocity really answer. If we're talking about acceleration, okay, it's how quickly velocity changes. Or another way of putting it, and if you get this, I feel like that's a good sign that you understand this difference, is how fast you get fast. Okay, that's a really good way of thinking about acceleration. Okay, moving on to some things we know about speed and velocity. So starting with the distinction between speed and velocity, keep in mind that speed is simply a measure of how fast, and velocity is a measure here of how fast plus direction. So this is the key thing that distinguishes speed from velocity. Okay? Moving on to our next distinction, which is distance versus displacement. So distance is a measure of how far an object travels, okay? And our displacement is going to be how far we are from the start, or from our initial point, all right? When are these two things equal, distance and displacement? They're going to be equal when we are traveling in a straight line. All right, so in that situation, however far we travel is how far we are from where we started. Our last distinction we have to make is the difference between average, which is over a period of time, and instantaneous, which, as the name suggests, at an instant, at one particular moment in time. Okay? So that's the key difference, and we can talk about that for lots of different quantities, but these two quantities, average and instantaneous, will be equal when we have constant, in this case velocity, but in general just a constant value, whether it's velocity, force, acceleration, anything. If it's constant, average and instantaneous are the same. Okay, putting some of this together, we arrive at our formula for average velocity and average speed. So average velocity is displacement, okay, the change in position over time, and average speed is distance over time. All right. Keep in mind that in general, speed is velocity without the direction. However, okay, average speed and average velocity are not linked in that same way. The average speed is not necessarily the average velocity minus the direction. Okay, it could be a completely different value. Okay, so some tips here when you're solving these problems. The one thing I would always start with is setting up a chart of what you know. Okay, this is slightly different than our kinematics chart, but we can look at delta x, average velocity and t, or distance, average speed and time. So a slightly smaller chart if we know it's an average speed, average velocity type problem. Okay, some other things to keep in mind. Okay, we want to think about if we want distance or displacement. And lastly, we do want to be careful with our units. All right. Last question here, when do we need multiple setups? All right. This is going to come into play if we have multiple objects. All right. So maybe we have two objects traveling at different constant speeds, or maybe we have multiple parts. Okay, we did a lot of problems where there was like the first part of the trip, the second part of the trip, and then maybe the third part of the trip, and also the total trip. So if we have those, we're going to set up that basic idea, that basic chart for each one of our parts. Okay, moving on to talking about motion graphs here. So on the very base level, we've got to know how to get information about position, velocity, and acceleration on each type of graph. This should be an instinct for you, second nature here. But we're going to go over it. So on a position graph, we simply read the graph to get information about the position. We slope the graph to get information about velocity. And we are looking at curves to get information about acceleration. On a velocity versus time graph, okay, the velocity we simply read, and the acceleration is the slope. Now, we can't actually get information about the position itself, but we do know that the change in position is the area. So we can say that on a velocity versus time graph. Digging a little bit deeper here, how do we know if the object has a positive or a negative velocity on a position versus time graph? That is going up versus down, okay, which really corresponds to a positive or negative slope. On a velocity versus time graph, we're looking at the y-axis. So if we are above or below that y equals 0 line, okay, which ends up being the x-axis. Speeding up, slowing down, on a position graph, we are looking at getting flatter or slopier. All right, so getting flatter like that or like that would be slowing down. Okay, getting slopier like that or like that would be speeding up. All right, and on a velocity versus time graph, we're looking at whether or not we are going towards or away from that x-axis. Okay, so slowing down looks like this, and speeding up is going to look like this. Okay, so here we have slowing down and speeding up. Last thing is positive or negative acceleration. So on a position versus time graph, we're looking at whether it is concave up or down. Okay, so remember, up like a cup means positive acceleration. Okay, down like a frown means negative acceleration. On the velocity versus time graph, we are looking simply at whether or not we have a positive or a negative slope. Okay. Last little bit here, looking at finding average speed, average velocity on these kinds of graphs. Okay. So for average velocity, we need displacement. So we need to find the change in position. All right. So on a position versus time graph, we're going to read the beginning and the end of our graph and find out what our change in position is. And on a velocity versus time graph, we're simply going to find that area, and that area is the change in the position or the displacement. It's a little bit trickier if we're thinking about average speed and we need distance. Okay, on a position versus time, all right, we're going to have to read it. But we're going to think about how far forward or back we go. All right, so I'm running out of space here, but if our position graph goes like that and then like that, we want to think about how far forward we go here and then how far back, okay? And add up those distances, because keep in mind with distance, okay, those negatives don't matter, all right? The fact that this portion is negative does not matter. And on a velocity versus time, okay, we're still going to find the area, okay, but just like how we didn't include negatives here, we're also going to not include the negatives when we find the area. All those areas below the x-axis we're just going to make positive. Okay, next piece here, kinematics. One thing to keep in mind for all of these, and we didn't do any problems where this wasn't true, really, but all of these equations only work for a constant acceleration. So we had 4 kinematic equations that we're going to put down here. Obviously, you'll have your equation sheet for the test, so you don't need to memorize them, but these are the 4 equations. So here we have our delta x, our VF equation, our VF squared, and our other delta x equation. So those are our 4 equations that we're going to have. Some tips for solving these. The first thing we want to do is we want to set up that chart that we have for this with the 5 variables, delta x, VI, VF, A, and T. Okay. We also then want to think very carefully about signs once again here. They play a huge role. All right. The other thing to think about too is read into the problem. Okay, and think about what concepts we know. All right, and what we're trying to find. One last thing to keep in mind, kind of keeping your back pocket here, is that quadratic trick that we talked about, the way to get around using the quadratic formula. And so the way we do that is we first rather than solving for time, and that's when it comes up, is when we're solving for time, we're going to first solve for VF using our VF squared equation. Okay. Then, of course, the most important step is we're to check our signs, all right, and make sure that they match logically with the problem. And then, once we have that, we're going to find t, and now we're going to use the VF equation, all right, to get that time. So that's our way of getting around the quadratic formula if you don't feel like doing that. Okay, moving on to our next part, which is free fall. The most important thing we know about free fall is that all objects in free fall are accelerating down at 9.8 meters per second squared. That's the most important thing we know. We do have some other concepts that are important here, so I'm going to start filling them in. So the first is that our velocity at the peak is 0, in addition to that acceleration being that 9.8 meters per second squared down. We also know at the peak that our time is half of our total time. Now you remember that one comes with the asterisk here. This is only true if it's symmetrical. Two other things we know: if it is symmetrical, we know that at this point here where it returns to its initial position, okay, the displacement is 0, and we also know at that point that our velocity is simply the negative of our initial velocity. Our next piece here, what is our acceleration at the peak? Keep in mind that acceleration at the peak is still 9.8 meters per second squared, and we say negative to indicate that it's going down. Some other important concepts and ideas, right? First of all, signs. Yet again, I know I've said that like 5 times already, but it's worth repeating, are going to be really important here. Another thing that's going to be really important, and this is different than just regular kinematics, is we need to really think about knowing when concepts occur. Okay, is this something that happens at the peak? Is this something that happens at the end? All right, you need to think about when those concepts occur, because that really matters here. And something else to think about related to this is use only part of the launch if needed. Okay, sometimes we only looked at going to the peak or from the peak down, and that was a really useful thing to do, so that's something to keep in mind. Okay, lastly, moving on to some of our complex kinematics problems, ones where there were multiple objects or multiple accelerations. So maybe we had a constant velocity and then we were slowing down, or maybe we had a police car and a speeder, all right, chasing each other. These are situations where we need multiple setups, all right, and that's really the key idea. Some tips for this, okay? We want to set up a chart for each object or situation, and by situation I mean acceleration. Okay? We want to think about links between the setups. Okay, and there's lots of possibilities here, but some things to think about. If you have a situation where it's one right after another, does VF become VI? Okay, are the delta x's the same? Are our times the same? Okay, these are just a few examples of things that might happen, all right, when you're doing these problems. And so these are things that you want to look for. The last thing, and I realize it wasn't in your printed up in your outline, but this idea of ratio problems, and it kind of goes along with complex kinematics. But these are the situations where we have initially it's v and then it becomes 2v or 3v. Just some things to consider with these. All right, set up two charts. All right, we have our old or original and our new situation. So set up a chart for each. Okay, we want to write relevant equations. All right, based on what we know, because we probably know some things. It's pretty doubtful we don't know anything. So we want to write those relevant equations and write variables in terms of others. Okay, so if we know that our time is 3 times as much, we would write t and then 3t. Okay. And then the final key is to combine the equations. And we looked at a lot of ways of doing this. Sometimes we can divide equations, we can solve for one thing and set equal. Sometimes the equation works out so nicely that we can just see the relationship and there's no need to do any of that. But the key is we want to somehow combine those equations. Okay, so we're going to begin our review here for our second test on Newton's laws, as well as some review from earlier. So we're first going to start with the new stuff, Newton's laws. So just some basic ideas about forces. Keep in mind that all forces are caused by objects, and most forces require contact. Moving on here to Newton's first law. So the first law tells us that unbalanced forces cause acceleration. That's the key idea. Balanced forces mean no acceleration, unbalanced forces cause acceleration. That is really what Newton's first law is. So if we have a situation with no unbalanced forces, that means our object is either at rest and will remain at rest, or our object is moving with a constant velocity and it will maintain that constant velocity because there are no unbalanced forces in order to cause it to change its motion. Moving on to the second law here. The second law is really just an equation. We can derive some conceptual meaning from it, but the second law is sum of the forces equals ma. So we can talk conceptually some about what that second law tells us. The first thing it tells us is that when we apply a greater force on an object, it leads to more acceleration. The second thing it tells us is that objects with more mass, okay, are going to require more force in order to accelerate at the same rate as other objects. Moving on to the third law here. So the third law tells us that forces come in equal and opposite pairs. So if we have our classic situation here where two objects are pushing on each other, object A and object B, we know that the force of A on B is going to be the opposite, so same magnitude but opposite direction of the force of B on A. Keep in mind that these two forces that we're talking about, this third law pair, they act on different objects, okay? You will never have a third law pair where the forces are acting on the same object. Okay, moving on to some other concepts related to Newton's laws. The first thing to keep in mind is that if you can't name an object creating a force, then there is no force, all right? So keep that in mind. You need to have an object creating a force. The other really big one to keep in mind is that objects can exert forces on themselves. So as you're going through trying to explain a lot of these, keep that in mind, those two big things. Okay, thinking now about some just general tips for actually getting into some of these math problems with F equals ma. We have a few things that we need to be doing every single time that need to become automatic.